Calculus AB 2019 AP exam, question number 4. Question says, a cylindrical barrel with a diameter 2 feet contains collected rainwater, as shown in the figure above. The water drains out through a valve not shown at the bottom of the barrel. The rate of change of the height of water in the barrel with respect to time is modeled by this function here, dH dt, where h is measured in feet and t is measured in seconds. The volume of the cylinder with radius r and height h is given by v equals pi r squared h. So I'm going to give you a little visual. Before we start to answer any parts of the question, I want to give you a little idea of what's going on here. Now, they didn't say how tall the tank was, so I just made it 10 feet tall, and I'm going to drain it, and it's going to drain at this rate. And you can see as it starts to drain, here's the rate of change of height with respect to time. And as the h gets smaller and smaller, obviously the rate of change is getting smaller and smaller. So therefore, you see the rate of change is getting lower, and it's going to start slowing down as it goes down. So as this thing is draining out, it's going to drain slower and slower and slower. And you see as it gets down to the bottom here, it's not going to be going very fast. And you'll see that the time it takes is going to be about 63 seconds. You see this is going very slow now. The rate of change of the height with respect to time is very slow. Okay, so now the tank is empty. So let me show you that another way, just to give you a little feeling for what's going on. I'm going to drop it 5-second intervals. So in other words, I'm going to go from 0 to 5 seconds, and we'll see how far it drops. And then I'm going to go from 20 to 25 seconds and see how far it drops, and then from 40 to 45 seconds. So just to give you an idea of what it means for the rate of change is slowing down. So we go down, we're dropping now from 0 to 5 seconds, so the time is going to go to 5 seconds. And you can see it drop from 10 to 8.48 feet, which is a change of 1.52 feet. So in that 5-second interval, it dropped 1.52 feet. Now if I go down to 20 seconds and then see how far it drops when it gets down to 25 seconds. So now from 20 to 25 seconds, it only changed, the change in the height was 1.02 feet. So it's much less than there. And then if we drop down to 45 seconds and we go from 45 seconds to 50 seconds, so a change of 5 seconds, you'll see that the height changes much less now. So just to give you an idea, so that's what it means, the rate of change of the height. So during these 5-second intervals, this is constantly happening every second, it's slowing down, but it gives you a good idea what's going on. In 5-second intervals, you can definitely see the chunks of change in the height of this tank. So now let's go and see if we can answer some of the questions. We got a little bit of an idea of what's going on here. The first part says, find the rate of change of volume of water in the barrel with respect to time when the height of the water is 4 feet. Indicate units of measure. This is pretty common. When there are units given to you, chances are there's going to be a point for units of measure. So you better make sure you're conscious of that. You don't want to lose a point for not putting the units down. So when I do these kind of problems, I mean, you should always think of what you're looking for, but we're looking for the rate of change of volume. We're actually looking for the rate of change of volume at a particular time or a particular event when the height is at 4 feet. And what we do know is we know the rate of change of the height with respect to time. So we're looking for rate of change of volume. This is rate of change of volume when the height is 4 feet. And we're given the rate of change of height with respect to time is minus 1/10 square root of h. So we're looking for this and we're given this. Now the way I usually do these, the way to help you set it up, we need an equation involving v and h, these two variables. And so you look for that. If you weren't given it, you should know the volume of a cylinder or some other equation that would give you a connection between those two variables. And so that's what we need. There's our connection. And so here's our volume equation. Now, one thing nice about this problem here the radius of the tank is not changing. It's not a cone, so the radius doesn't change as it goes down. It's a cylinder, so the radius is always 1. So anything that's a constant we can always put in. We will always love to get rid of any variables we can possibly get rid of. So now if the radius is 1, the volume is going to be pi times r squared, which is 1 squared h. So it simplifies the volume as pi h. And a lot of times, if it was a cone or something else, we would have some kind of a comparison, like it might say that the radius is twice the height or the height is twice the radius, and we could substitute and get it in terms of just two variables, v and h. That's what we wanted. We wanted in terms of just the two variables, v and h. So we've got it there. So now what we have to do is differentiate. Because we have the volume as pi h, we need dv dt, so we differentiate v. So dv dt is going to be pi, it's a constant, times the derivative of h with respect to t. And now dh dt, we know over here, dh dt is right here, so we're going to substitute that in for dh dt, which is minus 1/10 square root of h. So dv dt is equal to this right here. But now we're looking for dv dt when h is 4. So when h is 4, we plug 4 in for h, and we get here, this is square root of 4 is 2, so we get 2/10 or minus 1/5 pi. That's the rate of change. That's the rate of change at the instant. That's the rate of change in volume at the instant when the height is 4. Now something else, the units of measure, you can look at this, and again, you got to learn to look at units all the time. Volume would be, in this case, it would be feet cubed. And the time in this case is seconds. So the units of this would be feet cubed per second. That's how you can find the volume. And so here's our answer. Now when you answer the question, the rate of change of the volume of water in the barrel is changing with respect to time when the height is 4 feet. You got to include the 4 feet, because this is not the rate of change all the time. That's only the rate of change when the height is 4 feet, and it is going to be minus, which means the volume is going slower at that rate, and it's feet cubed per second. In part B, it says when the height of the water is 3 feet, is the rate of change of the height of water with respect to time increasing or decreasing, and explain your reasoning. Now, I like to think with simple generic functions, like if I said to you, when is f, some function f, increasing or decreasing, hopefully you would know that you'd have to find f prime. Because if f prime is positive, then the function f would be increasing. In other words, if the slope f prime is positive, it would be going up. And if the slope f prime was negative, it would be going down. So that's very simply. So in my thinking then, so that's what I think about. So when is f increasing or decreasing? When f prime is positive or negative. So if I'm looking for when the height of the water, when the rate of change of the height, I want to know if that's increasing or decreasing. That means I need to know the second derivative. In other words, whatever I want to know whether it's increasing or decreasing of, I need to know the derivative of it, the slope of it, the rate of change of it. So if I want to know when dh dt, which is the same as h prime, I want to know if that's increasing or decreasing, I need to know when the slope of this, or the derivative, which is the second derivative, which is d squared h dt squared, or h double prime, if that is positive or negative. So that's my thought process. So what I need to know here is I know dh dt, so now I need to know I need to differentiate it again. Okay, so here's this, we'll do the work on this now. So here's dh dt, I just copied it down here, and I need to differentiate this, so this is d squared h dt squared. Okay, that's the second derivative. And so I need to differentiate this side. So this is a constant minus 1/10. And then I'm going to differentiate this. So it's going to be, using the power rule, 1/2 h. So this is going to be 1/2 times h, drops a degree to the minus 1/2 power. And then I have to differentiate h with respect to t. So this is a chain rule. We're not differentiating with respect to h, we're differentiating with respect to a different variable t. So we're going to always have to use the chain rule there. So that's what the h squared dt squared is. And now dh dt, you notice, remember, see, dh dt is right here again. So we can substitute that in here. And actually, this works out very nicely for us. So we substitute that in for dh dt. So I just wrote it right here. And now we're going to clean it up. So if you notice this, we're multiplying three things. There's a negative here and a negative here. So it's positive. I have 1/10 times a half times a tenth is 1/200th. And I have h to the minus 1/2 power times h to the 1/2 power, which becomes h to the 0 power. When you're multiplying, remember you add exponents, so it's h to the 0 power, which is 1. So the second derivative, or d squared h dh dt squared, is 1/200th. Okay, so now what does that tell us? Well, the second derivative at this instant is, by the way, it's a constant all the time, but we're looking at the instant when the height was 3 feet, so it's true. So 1/200 is a positive number. Therefore, the h dt is increasing. And so now we just have to answer the question properly. And remember, when you answer these questions, make sure you include at what times or what instance this stuff is happening. So the rate of change of the height of water when the height of the water is 3 feet is increasing at a rate of 1/200 feet per second squared. Part C states at time t equals 0, the height of the water is 5 feet. Use separation of variables to find an expression of h in terms of t. So this is an initial condition at time t equals 0, the height of the water is 5 feet. And it's nice of them to tell us to use separation of variables. A lot of times they will not do that, and you need to know enough to use separation of variables. Okay, so we have dv dh dt here, so we're going to use that. So here's the h dt, and they say separate variables. What that means, you see there's two variables involved here. There's h's and there's t's. So that means separation of variables means we got to get all of one variable on one side. So h is on one side, t's on the other. And a good thing to be careful with here, we don't want to move the dh to the denominator on this side or divide both sides by dh, because then you run into problems. Leave the dh where it is. We don't integrate with the dh or dt in the denominator. So leave the dh where it is and multiply both sides by dt. So that gets the t's on this side, and then divide by h to the 1/2 power. So there's my separation of variables, and I'm going to clean it up a little bit. So I multiplied by dt divided by h to the 1/2 power. And don't get confused. This is not natural log. This is not du over u. This is du over h to the 1/2. So you need to move this to the numerator so it becomes h to the minus 1/2 dh. And now I have it separated variables, and I have it in nice form so I can integrate. So now I'm going to integrate it. So the integral of this, remember when you integrate using powers, you add 1. So this becomes h to the 1/2. 1 minus 1/2 plus 1 is 1/2. And then you divide by 1/2, which means you multiply by 2. I don't like to write the step down divided by 1/2 because most of the time you get confused with fractions and fractions. When you divide it by a fraction, you multiply by the reciprocal. So it becomes h to the 1/2 divided by 1/2, which means times 2. And by the way, well, then you get here, we have minus 1/10 as a constant, and the integral of dt is t, and then plus c. Now, don't get confused here. I integrated both sides, so you integrate this side, you might say, why didn't I put a plus c over here? Well, think of it. If I put a plus c, it would be different, so I put a plus c1 here and a plus c2 here, and if I move the c1 over to this side and added c1 and c2, I get another constant. So it is acceptable when we're doing the separation of variables and integrating two sides, we just put the constant of integration on one side. And to me, it's always smart to put it on the side where the t is, because we're solving for h, the side away from the one you're solving for, because that just saves us one more step. Okay, so the next thing we have to do now we have to use our initial condition at t equals 0 seconds, we're at 5 feet, and find c. So we're going to use this initial condition that was given to us, and that's how we're going to find c. So when t is 0, the height is 5 feet. So this becomes 2 squared of 5, and 0 times 1/10 is 0, so c is equal to 2 root 5. And now we have to just plug this back into the equation and then solve for h. That's our last steps. So I just rewrote this equation over here. Then substitute C. We found C to be 2 root 5. And now solve for H. So the first thing we need to do is divide by 2. So you distribute. So you're dividing by 2, so this becomes 1/20th. And you divide this by 2, and the 2's go out, so you just get root 5. And then I need to square both sides to get rid of the 1/2 power. And you need to square the entire side. You cannot distribute squares or square roots. You can only distribute multiplication through addition, subtraction. Okay, so this becomes H, and this entire side here is squared. So we now have solved H in terms of T. Now let's look at what they gave us the points for. The first part, they gave us 1 point for dv dt, which was pi dh dt. They gave us 1 point for our answer and the units. Now, if you didn't have the units there, you'd lose that. You'd do all this work and you'd lose that point. So make sure you put units down. Part B, they did the chain rule differently than I did it, but so you would have gotten, if you did it the way I did it, you'd have gotten 2 points for d squared h dh dt, d squared h dt squared, and this is what we got, and then 1 point for the answer, which was 1/200, and making sure you state it's greater than 0, therefore the rate of change is increasing at this instant when the height is 3 feet. For part C, we got 4 points, 1 for separation of variables, so 1 point for getting the variables on opposite sides, 1 point for the antiderivatives, okay, and then 1 point for using the constant of integration and the initial condition. So if you didn't put the constant of integration down, you'd lose 2 points, you wouldn't get any more. And if you didn't separate variables, by the way, you'd lose all 4 points. And so you get 1 point for using the constant of integration and the initial condition and getting C to be 2 root 5, and then 1 point for solving for H of T.